Hello everyone. This video tutorial is about 2D steady state heat transfer analysis in Abaqus. This is an steady state problem and it is taken from book Finite Element Analysis Theory and Application with ANSYS and Chapter 9 Analysis of Two-Dimensional Heat Transfer Problems, and then topic 9.7, that is steady state example. So that one example from this is an example, solved example in that book. So a chimney constructed from two different materials. The inner layer is constructed from concrete with thermal conductivity of 0.07 BTU per hour inch degree Fahrenheit, and then outer layer is from the bricks with thermal conductivity. The temperature of hot gases inside surface is 140 with a convection heat transfer coefficient of 0.037 BTU per hour inch square degree Fahrenheit. The outer surface is exposed to the surrounding air having temperature 10 degree Fahrenheit with a corresponding convection heat transfer coefficient of 0.012. Dimensions of chimneys are shown in the figure. So here the inner is concrete. Its inner side is in the form of a square. Inner side is 12 inch and its thickness is 1 inch. So the outer side will become 14 inch. And for the bricks, inner is uh, again inner is a square 14 inch and the outer is 26. So in this problem, uh, to determine the temperature distribution within the concrete and within the brick layers under steady state conditions, and then plot heat fluxes through each layer. So to solve this problem in Abaqus, here are steps. So before starting in Abaqus, first step is to check the units. So the first set of unit that dimensions in meter, then temperature in as K, thermal conductivity, watt per meter Kelvin, and then heat transfer coefficients, watt per meter square Kelvin. And the second one, dimensions in feet, temperature in Fahrenheit, then heat transfer rate as BTU per hour, and then these are the units of heat transfer rate and thermal conductivity. So in this example, the units are dimensions are in inches, so it doesn't make any difference. So no need to convert them into feet. Okay, so the first step before starting is in Abaqus is set work directory. And I want to save that in this chapter, in this folder. I'll just copy link from here and then file set work directory. And I'm going to set that work directory here. Okay, so now work directory is being set, and then the first step is to create part, and in this it will be shell planner. So create part. Here the parts will be can be created as two different parts, one for concrete and the other one for bricks. So the concrete, so for that one, uh, double you can double click on here or just simple click on here. So part one is concrete, and it is a 2D planar problem. 2D planar, 2D planar deformable shell. and approximate dimensions of that are double of, like it is 20, 12 inches. So for 12 inches, it may be 15, so, or let's say 20. Okay, so now is a 2D planar. So for that, two squares are required. The inner one with each side as 6 inch and the outer one with 7 inch. Okay, so this one rectangle 4 line can be used for, so its coordinates 6 and 6, and the other one are -6 and -6, so that is being created, and the other one with the coordinates 7 and 7 and -7 and -7, so that is being created. Then to check the dimensions of that, so here auto dimension, select the entities to dimension, then done, and here you go. For the inner one, it is 12, the outer is 14, and then the thickness is 1. So done, and that first part has been created, and I can, so this part which is created, it is concrete. Now the second part is bricks. So second part 2D planar deformable shell, and it is like 26 inches. So I can go like 40. Continue, and then again I'll start from there. So inner 14 by 14 side, so that one, and outer as 26 inches. So it is again a square with 13 and 30. Okay, so then it is being created. So dimensions can be added from here, auto dimension, and then done. So 26, 14, and then thickness of that is 6. So done, and then done. Okay, so now these two here in the part, brick and concrete, they are being created. Okay, now the next step is need to create surfaces. Why surfaces are required? Because for inner surface, that temperature and heat transfer coefficient need to be defined, and then inner surface, outer surface of concrete and inner surface, they are being joined by a link, oh sorry, by some interactions. So the next step for each one, surfaces are required, and for that one here, for brick, here is like part, and then here break, so surfaces. So then it is inner surface, continue, and that is the inner surface. So done, that is inner surface. You can see in the surfaces that inner surface has been created. Now the outer surface, so that is for break, outer, continue. I select these two edges, and with the shift and mouse other two, so that outer surface is being created. So now for the surfaces, I expand it. So that is the inner surface, that is the outer surface. Now for the concrete, here is concrete and again surfaces. So for concrete, it's inner surface, continue, and then that you are done. That is the inner surface. And then now outer surface, continue by selecting these edges individually or like that way using shift and mouse. So then now that surfaces are being created. So these surfaces are used to apply boundary conditions or to apply temperature and to connect to different parts. Okay, So after that, uh, this one, create Datum plane and then partition. So this specifically is required to determine the temperature distribution within concrete and within the brick and plot heat fluxes through each layer. So that temperature distribution either like from the center and outward or from this point to rightwards. So for that one, this part is just is if temperature distribution or heat fluxes are not required, so then this step is not necessary. So what I'm trying to do is I try to plot that heat fluxes and temperature distribution right from the center and outward. So for that purpose, I need to create a here in concrete Datum plane I am going to draw and then I'll create partition on that. So then for that purpose, here are these are like this one. It is a partition face, but what I'll do here, this one, there are different options, offset from principal plane, and then this one is midway between 2 points. Okay, so midway between 2 points. So I want to create a partition here in between, midway between these 2 points, so that Datum plane has been created. And for concrete, here that in the feature that Datum plane has been, so that is the Datum plane. Now the next one, to create partition, tools, partition, partition face using Datum plane, and then select a Datum plane, and that partition has been created, done. And this Datum plane and partition, they are just to select number of nodes to plot distribution. Otherwise, that's not necessary. Now, once concrete done, now the same one for the bricks. So here, tools, Datum, a plane, and then midway between 2 points. So that is like here. So that is the way, or you can also create a Datum plane midway between these 2 points. Okay, like that way, but it's not necessary there. And here in the bricks, like this is one Datum plane, and that is the other one. Okay, like this is the first one, that is the second one, that's not required, so I'm going to delete that one. Okay, now here I can create partition, so that is the partition face, and then there are different options here. Select a Datum plane, so Datum, and then create a partition, done. And you can see here, so a partition has been created. So the only purpose of creating these partitions, so to get nodes on a specific path. Okay, so once partition has been, now the next one is create material, next step. And there are two materials. One is for concrete and the other one is for bricks. Okay, so then here in the property module, or by just double clicking here in the materials, so create material, concrete, and then thermal conductivity. So thermal conductivity of concrete is 0.07. 0.07, that is the thermal conductivity of concrete. Then another material, bricks, and in properties thermal conductivity, and for that one is 0.04. So that is a thermal. So two material has been created, so I can double click on bricks to get that thermal conductivity of brick is 0.04, and then for concrete it is 0.07. Okay, so in the same, uh, create material, after that create section, and then assign section. So then here is create section. So two sections are required here. The first one is concrete, and then material for that is concrete. Okay. And the other one is bricks, solid homogeneous, and then here bricks. So two bricks, that is a solid homogeneous with the material brick, and then concrete is that one. And then assign. So bricks, bricks, and then assign. So select that one. So because part is bricked open, so I'll assign it as bricks. Okay, so done. Now concrete, assign section, and then done. And then that concrete is being assigned to that one. So now materials has been assigned. Now the next one is mesh. So now here in the module, that is mesh. So the first step is to seed part. Here the first step is seed, then mesh part and assign element type. So the next seed, assign mesh control, mesh part and assign element type. So the first one is seed. So that is concrete. Then this one seed, seed part, approximate global size, that is 1 inch. So I don't want that higher. I will go for point, point 0.2 inch. 0.2 inch for both concrete and brick. So that is being applied. So it is a little bit finer mesh. Okay. And then before that, assigning mesh control. So mesh control, it's select the region, done, and then quadratic and free. I'm just going for free. Okay. And then yes. So with the free mesh is not a very good option for this one. So I'll assign mesh control again, and then here quad, and not advancing front. Algorithm is medial axis. So medial axis I'm going to perform so that I'll get a very good meshing. So in here, like once again, like, okay, I'll explain in the other model. So then assign element type, select the region to assign element type. So that is selected, done. And then standard linear, and the family is heat transfer, and it is DC to D4. That is a basic one, a 2-4 node linear heat transfer quadrilateral element. So that is done. Now the mesh for concrete is done. Now for brick, again seed part, and let's say 1, apply. So that will be coarse mesh. So I'll go here 0.2 inch, apply. Okay, then mesh controls, it is quadratic, free, and medial axis. So okay, and then mesh, so that is mesh. Then element type, so select that one, done. And then standard linear in the family is heat transfer. Okay, quadratic, and then DC to D4. So that is done. So now in seed, assign mesh control, mesh part, assign element type, all done. And then I'll create set. So to plot that distribution, so I'll go back to the part, and then on part, I'll create set. Okay, so here concrete, and then concrete, and then you have set here. So double click on that. So set one, yeah, it is that set is concrete node, and then after node make unsorted set. Continue, and then you have here either you can show here node labels, or is a very simple way you can select a picking method for inserting selection, so free, and then here because it's the first line, so I'll say add before, and then it's select node. So I'll select node about that datum plane. Okay, so done, and that one a set of nodes has been created, and then you can see it is being highlighted. Then the next one is for brick, the same one, the break in bricks, in bricks. So here, so set and then node, unsorted, make unsorted set of the nodes, so continue, and then here for that one is bricks, and here picking method is free, add before, and then this one nodes about that edge. So that's done, and now sets has been created. The next one is assembly and create instance. So assembly module, here create instance, brick and concrete. Okay, so now you have these two instance, and then like in the part instance or like part, so that is concrete, the outer was is brick, or otherwise you can, if you are using that assembly defaults, so in assembly just that is brick and that is concrete. So the next one step, and in step it is a heat transfer. So here in the module step, create step, and that one is just heat transfer, and here is heat transfer continue. So response is steady state because we are using that steady state heat transfer, and then the rest will all stay, and the time period is just 1 second. Okay, so now step has been created here. You can see it here. The next one after that is we need to join these two parts, and for that purpose, for that one, it is in the interaction module, create constraints, or just in constraints. So like as here, so let me close that part, and now here constraints, just one constraint, double click on that. Okay, or otherwise in interaction that is create constraint, and this one constraint one, let's say. So and then constraint is type. So it says that choose a master type. So usually in heat transfer, the master is a hot surface or a source, and slave is a cold surface. So choose a master type is a surface, and then select the region for master surface, but I have already created a surface, and that is inner surface of concrete. So that is concrete inner surface, that is a master one, and then a slave surface is a surface, and then that is brick inner. Continue, and then it's, it has few options. So it's a position tolerance. So use computer default. I'm leaving it as it is. Okay, so whatever is the defaults are there, so then it is no. So There was a mistake, I rectified it. So master surface is concrete outer and slave surface is brick inner. Okay. So now you can see that those yellow circles for constraint, and that is a constraint. After that, uh, create interactions, and with these interactions, so here you have interactions, here interactions, or you can go into the module interaction and then create interaction. So create interaction, so that is for inside of those interactions are required for this inner surface and then overall outer surface. So then outside, let's say outside, and then is step is heat transfer, and if you try initial, so it will not give you that what is required, so heat transfer, and then there it is surface film condition. So here you have surface film condition, continue. Now it says that select surface, so then it is concrete inner, concrete inner surface, continue, and then film coefficient, that is uh, coefficient for inner one, the coefficient is 0.037 and temperature is 140. So that is 0.037 and the sink temperature is 140. Okay, and now you can see that rectangles there. I'll create another, and that is out. Sorry, in interactions, let me rename it. It is inside. That is inside, and then another interaction outside, and again step is heat transfer, surface film interaction, and then that is break outer surface. Continue, and film coefficient for that outer surface is 0.012 and the temperature is 10. So for outer surface, it is point heat transfer coefficient is 0.012 and temperature is 10. So 0.012 and 10. Okay, and now you got that interactions. So all that necessary steps for modeling, they are being performed. And then the next step is in analysis to create job, data check, and submit. So jobs, and before that, I'll name it. It is, I'll rename that. It is steady state heat transfer example. The steady state heat transfer example. Okay. And then in the job, I'll give the same name, steady state heat transfer example. Continue. I'll leave that everything as it is. And then data check. So history output is not requested in the following step. So okay to continue, yes. And then it's being check submitted, then running, and then it takes some time to complete. Now check complete. Now I can submit it. So it says that history output is not requested, just okay to continue. And then it's submitted and it's running. And after some time, it will. So that is completed. Now I can go to the results and then visualize results. Otherwise, you can go here, open, and then that ODB you can also open, and here you'll have that mod ODB. Now that is the deformed shape, and here you can go here, that is HFL, heat flux, node temperature. So that is, and then that is the node temperature. Okay. So, and that is a temperature gradient along that one, and that is the heat flow. So next is determine the temperature distribution within the concrete and in the bricks layer under steady state condition and plot the heat flux through each layer. So I want to draw somewhere here. So because it's metric, so here will be the same, but along that corners it will be different. So for that purpose, so once it's all done, so I'll use here labels. So show node labels. Okay, although it's too much to show there. Okay, so that is too much to show there, but I am interested in these ones only. I'm interested in these ones only. So for that purpose, what to do? Then in the tools, create a path with those node list. So tools here, path, create a path from the node list, continue. Now I want to create three paths, one for concrete, one for uh, bricks, and then one for whole part. So it's a bricks, yes, so node labels. So for bricks, I have already node labels. So node set selection, I'll add before, and then here I have brick. Okay, so now you can see for bricks. So it is in a sequence. Okay, so the nodes here are in a sequence, but in the model they are not in a sequence. So that is a 7, then 13, 14. So just to shift that 8 from the start to end here. So now if you click on that, so that is a path is being shown, so that okay, and that path has been created. Now the next one I am going to create in the manager. So edit that path. Okay, so no need of it, and then create another path. But this time the path is for concrete only. So I'm going to name it as concrete, and it is from the node list. Continue here, concrete, and I want to add here node selection, and then I have here concrete. It's being added there. And now again, it is here, it is a sequence, but I want this sequence from in the direction of heat flow. So there is 8 that is being hidden in here. So then this 8 node for from here, I need to also okay. So now you can see that is the start and that's the end. So that is now concrete path is being created, and similarly, the third path also need to create, and it is starting from concrete and all the way towards brick. So create path 3 is uh, overall, let's say, or both, or overall. Continue. Then I'll start from concrete, which is the inside, and add before here concrete that is being selected. Okay. Then add after. I need to remove that. Add bricks there. Okay. And now you have that. And in the similar fashion, need to put that 8 on the in the end. So now you can see that is the start and that is the end. So 713 for concrete. So that third path had been created. So now dismiss. So I am going to now remove that node labels, apply, okay. And sometimes we don't need that fine mesh. And for that one, common option again, and then visible edges, only featured edges. So that you will have that. Okay, so only visible edges you can see, or then, okay, so now here I have NT1, that is the nodal temperature. I want to plot that. And here you have create XY data. Here is the path, source is the path, and then path is the first one, let's say for concrete, and because here we have NT1, so it will plot that concrete. And here you can see it is from 0 to 1, 2 distance or X distance. I can plot that, and then sometime X coordinate, because X coordinate are from 6 to 7, and that is the temperature, and the maximum temperature is 124 and 116 is the minimum temperature. So similarly, I can plot for the bricks the same one. So for the bricks, the temperature is 116, 728, and 45. And then uh, that is the two distance I, or along X. And then for overall, so for overall for both concrete and brick, so that is plot. And this one, the background I can change from here, and you can fill different options for. Okay, so the temperature for overall in that path, it is overall for that path is 124 and 45. Okay, so for heat transfer flux, that is the heat transfer flux. If I want to plot it, so that is this one is for heat transfer flux. Okay, and then that is the temperature gradient is being plotted. So that one for overall, that is the temperature gradient. Okay, so that is now the what's the maximum and minimum temperature for that one. Uh, I go to the viewport annotation options, and then here is legend, this legend, and I here show maximum and minimum, and then engineering on that. So apply. So the maximum temperature, nodal temperature is 124, and the minimum is 19.79. So in the book, they have they have solved it using ANSYS, and the maximum temperature is 124.66, and the minimum is 19.877. So they are a little bit closer to that one. And now there is a temperature gradient. So the minimum value is here at the interface, which is about 7, and the maximum is 13.49 again on the interface. That is the temperature gradient. And then in the book, that temperature gradient is actually starting from 7.9. It goes then to 13, and then it is around 8 on the outside surface, and that is around somewhere around 8 or 9. So these results from this analysis, they are in line, or they are very much similar to the book. I hope you like this video. Thank you very much for watching. You can leave comments for feedback.